In the emmetropic eye, which is described as 20/20 vision or perfect vision, everything is right. The axial length from the cornea to the retina is about 24 millimeters to 25 millimeters. The cornea is shaped just right, and the crystalline lens is supple and clear. As light reflects off an object and travels into the eye through the pupil and the crystalline lens, it is refracted by about 60 diopters of power. 40 in the cornea, which is fixed, and 20 in the crystalline lens, which we can adjust with the ciliary body muscles. In emmetropia, all this light focuses on the fovea in the center of the macula. Small variations in the shape of the cornea can cause the light to focus a little too early or a little too late. If all the light focuses at a single point, we can easily correct the error with a spherical lens. If some of the light focuses at the retina and some elsewhere, either in front of or behind the retina, the condition is called astigmatism, and in order to correct the refractive error, we need a spherocylinder lens or a lens with a cylinder curve. With a simple spherical double convex lens, like you might find in a magnifying glass, there will be both magnification and distortion like you see here. The magnified text tends to be clear in the center and get more and more distorted toward the edges. We know from our study of lens basics that the power of this lens can be determined from the focal length. To get the text to appear clear, we had to move the lens until the distance between the lens and the text card was about 1/2 meter. Using our knowledge of the inverse relationship between focal length in meters and lens power in diopters, we can calculate the power as 2 diopters. Magnifying power can also be approximated by dividing the diopters by 4 and adding 1. In this case, our 2 diopter lens has a magnifying power of 1.5 times. But that is not the main point of this video, so let's move on. Now we're looking at a meniscus-shaped lens, which much more closely resembles what you will find used in most eyeglasses today. The lens has a convex curve on the front, which is called the front curve or base curve. It has a concave curve on the back, which is called the back curve. And we know that the power of a lens like this is determined by adding the power of the front curve to the power of the back curve. We're working our way toward an additional curve on the back called the cylinder curve or cross curve. The term cross curve stems from the cylinder curve being cut into the lens at an angle relative to the other curves. Try to imagine that a spherical lens is made from a cross section cut out of a sphere. The sphere used determines the front or base curve of the lens. Then imagine a spherical cutter that comes in and cuts another spherical curve on the back side of the lens. A spherical lens like this has no real orientation. It can be put in the frame in any direction, or to put it in optometry terms, the power will be the same on all meridians. Now all we need to do is have a cylindrically shaped cutter come in and cut the cylinder curve right across the spherical curve that is already there. The cylinder curve will be cut at an axis angle, and now the lens is spherocylinder to correct for astigmatism. It must always be put in a frame so that the angle of the axis from the horizontal is preserved. It will have no cylinder power in the axis meridian, and its maximum power 90 degrees away from the axis. So if the axis were 45 degrees, the maximum cylinder power would occur at 135 degrees. By the same token, if the cylinder curve is put on an axis of 90 degrees, there will be no cylinder power at the 90-degree meridian, and the maximum cylinder power will be at the 0 or 180-degree meridian. The lens now has the characteristic spherocylinder profile as seen here. Since we know from our mantra that the thicker the lens, the higher the power, we can see the high power and low power points of the cylinder curve. To solidify the idea of cylinder power, we now look at a glass cylinder in front of the reading card. Notice that on the axis of the cylinder, the text is seen without refraction, and we can see that at 90 degrees to the axis, cylinder power is at a maximum. The power varies from 0 on the axis to maximum 90 degrees away, depending upon the curvature of the cylinder that we put on the lens.